Thank you, Rachel. Please do make sure you reach out to us if you have any trouble getting those activated, because that's a critical component of this class. How's in-person lab going? Yay, in person. You make some copper oxide? That's a cool lab. I like that lab a lot. Get to look at them under the microscopes. Cool, excellent. If you haven't yet, please do return your lab kits from week 2. That was to Mike or DMart at the stockroom. And last but not least, this announcement is going to change, actually. I have asked Professor Fleshman to take over for me so you all can meet in person and we can make use of our beautiful new room. So Friday's class will be in person. Professor Fleshman will be running that lecture because she's eager to get a chance at the new room and wants to try it out for herself. So she's gone ahead and she'll be meeting you all there in the room, and I will be there in spirit myself. We will probably be back to Zoom next Monday, although that may be different depending on test results. So keep your eyes on the Canvas site for Monday's announcement. And last but not least, we'll be back in the new room by hell or high water next Wednesday. So today, we just got a couple of lectures and a little Chem 101 practice for you. So without further ado, Rachel or Mike, would you like to interject anything?
I've got one. Just a heads up, if you've never looked under the practice tab on Chem 101, we do make a practice assignment where we've dumped in lots and lots of extra problems. If you'd like to work through some of those on your own before the quiz on the weekend, you're always welcome to use that. About a dozen of you have taken advantage of it. Not required, but always a good and useful resource.
Yes, indeed. Practice, practice, practice. Highly recommended. And of course, those problems are perfect for bringing to open hours as well. So if you are working on those practice problems and need a little juice, that's just fine. That's a good place for it. So, all right, everybody, to today's topics. Don't have my usual screen here, so it will take me just a moment longer than usual to get things running. Okay, so I want to start with a recap from last week because we're getting into this stuff that's really counterintuitive, right? It doesn't feel exactly like you might expect it to from our kind of classical experience of the world. Okay, so we talked about light and electrons being like waves and particles. Something I think is really helpful to keep in mind is light and electrons and everything actually has both properties, right? Waves and particles. But there's a few things that make it so that we can think about them in one regime or the other, which is to say, when we look at really high energy light, like a gamma ray, that ionizing radiation, that's an important idea, right? That really behaves like a particle. So somebody help me out. Ionizing radiation, high energy light, does that have a long or a short wavelength?
A shorter wavelength?
Yes, that's right. So higher energy, shorter wavelength. In fact, that ionizing radiation, when you start to look at it, has a really, really, really short wavelength. And as that wavelength gets tinier and tinier, we start to see more and more particle-like behavior. So higher energy things tend to act like particles. We can kind of conceive of that when we use this idea of ionizing radiation, right? It's so energetic that it comes in and it blasts away an electron. It's like two particles crashing into each other, and there you go. On the flip side of that, we have things like radio waves. We don't think of radio waves. They are certainly not ionizing radiation. We all know that because we all exist in a sea of radio waves, especially in 2022 with your 3Gs and your 4Gs and your 5Gs soon, I guess, maybe. All of that's radio waves, microwaves, non-ionizing radiation. And really those just have much more wave-like behavior. They really don't act like particles to us. And if we think about that, we can think about that wavelength is huge. It's bigger than we are sometimes, right? Radio waves sometimes have wavelengths in the meters. And so that should make that we usually think of those then in terms of wave-like behavior. You hear interference on your radio and so on. All right. Next thing we got into was talking about how light interacts with our atoms, which is specifically that we see specific energies of light given off by hot atoms, and we see other atoms in their pure state absorbing light of a specific energy. We see these lines, just as like I have here, these 3 emission spectra. Okay, and that led us to our Bohr model of the atom. Electrons must have these quantized energies. He thought about it kind of from a classical perspective as if it was an electron orbiting the nucleus in a certain orbit, and as the orbit gets farther away from the nucleus, the electron has more energy, and we can say that lower orbits have lower energy electrons. And that gave rise to this equation here. This is our Rydberg equation, which we found useful for figuring out how much energy we should expect electrons to emit or absorb. And in fact, it explains the hydrogen emission spectrum very nicely. All right, so let's dig in a little deeper. Let's keep going. Here's a few questions in a row. And I'm sorry, these were supposed to animate it. If electrons are waves and particles, and they have energy, and there are infinite number of levels, right? We saw that n, where we have the different circles, the different orbits, we said n can be any integer up to infinity. Well, how do we ever get things like sodium plus or yttrium 3 plus or these ions that we know about from when we learned about nuclei, right? We had to learn about how many electrons does something have, how many protons does it have. In other words, can light ever remove electrons? And any of you who know about Albert Einstein, his Nobel Prize shows us the photoelectric effect. And the answer to this question is yes, it can. Let's do that. Let's think about how much energy is required to ionize a ground state hydrogen atom. Okay, so we'll keep with our really simple picture, the Bohr model of the atom, a single proton, a single electron. We could figure out how much energy is required to remove that hydrogen. Let's start with our Rydberg equation. Only let's do a trick, right? So normally we would choose a final level that's a certain value, and we have an initial level that's a certain value. Well, let's say, okay, so here's a couple important terms. We've got ground state here, right? This ground state, sorry, that's a bad underline. You get the idea. I was trying to underline that. A ground state is the lowest energy state of the hydrogen atom. So what does Ni equal in our ground state? I saw people in the chats before, so feel free to type it in the chat or shout it out loud.
1.
It's 1. Yeah, it's our lowest energy state, which is the one that's closest to the nucleus. The electron has the least amount of energy in that case. Okay, so that's helpful. That gets us going in the right direction. And this is a rephrasing of the same equation where I've taken Planck's constant, the speed of light, and the Rydberg constant, and I've turned them into one overall constant. And the useful thing about doing that is we can see what happens to our units, right? So we have meters per second for C, Planck's constant. I shouldn't have done this by memory. When you cancel out all the units, you can trust me, they end up with joules, right? So here we have joules for our overall constant. And then we multiply that by our initial and final states in this form here. So what should we use for a final state if we take that electron all the way off of the atom? Let's try using something like infinity, right? An infinite distance away from the nucleus is essentially like saying it's not there anymore. And for those of you who remember your limits from pre-algebra, 1 divided by infinity, the limit of that is going to be 0, right? So we can take this term here, and that will end up being 0, giving us, and since it's from our ground state, our n initial is going to be 1. So our n initial is 1, our n final is infinity. When we divide by infinity squared, we get 0. So the value inside the parentheses should simplify to -1, which gives us overall the change in energy for that electron is 2.178 times 10 to the minus 18th joules. In other words, if we have a photon of that energy, we can give that much energy to the electron and it will leave the orbit of the nucleus altogether. And that term there is something we're going to call ionization energy. And of course, our units are joules. Any questions on that work, how we would get there? Okay, a brief interjection, because, and I got to get rid of these annotations. If we go back and look at this number, that's a lot of 10 to the minus 18th. That's kind of a pain to have to always be writing that. And as we are starting to see, a lot of the times when we're dealing with atomic and nuclear processes, we're in that very small amount of joules. And so one thing that chemists and physicists like to do is make units more convenient, right? And so the joule is good for macroscopic processes, but these microscopic atomic nuclear scale processes, the electron volt is a beauty for a unit. Okay, and this is literally how much energy an electron has if it goes through 1 volt of change of electric field. You don't really have to understand what that means, but just recognize that it's a unit of energy. Electron volt is a unit of energy. And here are a few different energies that you might be somewhat familiar with. So there's the one we just did. The ionization energy of atomic hydrogen is right here, 13.6 eV. That's a lot easier to write than 2 point something times 10 to the minus 18th joules. We can see that dissociating sodium chloride into ions, something we're going to get to later in the term, is less energy, right? So taking 2 ions apart is less energy. But all these photons that we've been looking at in the visible, 1.5 to 3.5 eV. Okay, so there's a new unit for us that's a little more convenient. Again, we're in the single decimal point range. I like that. That's convenient. And this is also helpful for us to think then visible light is generally not ionizing radiation. Indeed, that's true. 13.6 is too high. We need more energy in our light than that. So we have to head into the ultraviolet or higher. So UVC is probably the first place you start seeing ionization energies, and it depends on the atoms. Okay, some other things you can look at through here too. Some of the energies for the nuclear decays that we were looking into earlier are really high energies, right? Mega electron volts. So there the joule is starting to be a more helpful unit. Okay. All right, so let's look at our diagram again and keep thinking about ionization energy and what this means to us. And one other way to look at this would be to put the energies of each of these levels. This is for the hydrogen atom now. And here are our levels at the very far right in N. We have the first level, that was our ground state. First excited state is level 2, 3, 4, and 5, and so on. And you'll see that one of these numbers, these kind of look like random things that people, there's a trend, obviously. This is the largest magnitude number at the bottom and the smaller one is toward the top, right? But it's very special to see here at the top, 0. That's at infinity, okay? And so this is something we do a lot in chemistry when we don't have a specific quantity to measure against. And sometimes even when we do, we'll set something to 0. We'll say, okay, well, I want my 0 point to be this energy. And in this case, for our ionization energy, we can do that. When we look at the energy levels and we try to apply an energy to those levels, we would say that this one here is our 0 state, meaning when an electron is in that energy level, it is given no energy, okay, or it has no change in energy. And then by the time the electron finds its way back down into that ground state, its energy will be reduced by this value here. All right, so what I kind of want you to think about is just how this is all relative to a certain point. And like I say over here, one of these numbers is kind of special, that 0 number. And it's always helpful to know what a 0 means in chemistry, in physics, and science, generally speaking. 0 tends to be special, so it's useful to know what we mean when we say 0. So when we say 0 here, we're not saying the electron has 0 energy. We are saying that the electron has its energy changed by 0 by being in that state. We would say that the electron has its energy changed by minus 2.2 times 10 to the minus 18th joules when it's in this state. Okay, and then lastly, the other special one then is going to be the other bookend, we might call it, right? So we've got one end, that's The electron is not even talking to the nucleus at all. It's completely off in outer space. The other one is when it's at its ground state, its lowest level. So that one's going to be down here. That's our 13.6, our ionization energy of hydrogen. And we can use that as kind of a referential number too. That's kind of a helpful one. Okay, and when we look at that, we can use some of the work by Bohr and have another equation here that gives us an equation for any one electron system. The energy of level n, to be put on a chart kind of like this one, is equal to negative k, that's a constant, times z squared over n squared. And we can use this for other atoms. And k, very importantly, is this number right here. Sorry, joules should be included in that. Aiden, you have a question?
Yeah, so we have right now we have a lot of equations. How do we know when to use which one?
This is a great question. It's the question, isn't it? How do we know when to use which equation? Well, it depends on the problem. And if you carefully read the problem, and if you understand your equations and what they're telling you, thinking carefully about what the variables in the question are and what the variables are in the equation, you have to kind of sort it out for yourself. That may be, for some people, the big challenge in chemistry, and that's great. That's why we give you all the practice problems. That's why you have homeworks for you to try so that you can start learning to parse out the questions. And in fact, how about we just jump right in? Everyone want to do that? Let's do a couple practice problems together.
Wait, can you go to the previous slide? I need to write down
Certainly.
the equation.
Yep.
Thank you.
And if you, while you're at it, you might as well write down what K is. K is equal to negative 2.18 times 10 to the 18th, negative 18th joules. All right, I say down here, can even use on other atoms for Z effective. So one of the limitations of Bohr's model that I spoke about a few lectures ago is that it's only good for electrons, or sorry, for systems that have a single electron. We're going to see on the practice problems on the next slide that we can use it. There's a way we can use this for systems that have more than one electron, and that's by using something called Z effective, which is, we'll introduce that on in the next practice problems here too. Okay, everyone good to move on? Speak now if you would like me to stay here for just a moment longer. All right, so calculate the ionization energy for a hydrogen-like atom. And when we say hydrogen-like here, what we're talking about is we're talking about a single electron, which it states right here in the problem after that, hydrogen-like atom with one electron and Z equals 3 from the excited state of N equals 2. Really quick, what does Z equals 3 mean?
Does that mean like the third orbital?
Okay, that would be N equals 3, right? Our orbits are denoted by N. So we can jump ahead just a little bit. The excited state of N equals 2. All right, so Aiden, you're right. You're scanning already the problem for the proper variables, and we landed on 1. Okay, so N equals 2. Anyone remember what Z is? Maybe from prior lectures too. So Z is going to be our number of protons, or our nuclear charge. So let me ask you another question. That's a meta question. If Z equals 3, what kind of nucleus are we talking about? Oh, see, I have lots of mugs. I didn't use the right one today. I should have used Z equals 3. We got to go to our periodic table. Let me pull one up. There we go. Ah, Mackenzie's got it. Thank you, Mackenzie. Yes, it is lithium. And of course, the periodic table image I tried to get to, right? So we just go back to our periodic table. Z equals 3. We have 3 protons, so 1 hydrogen, 2 heliums, 3 must be lithium. All right, so this is a lithium nucleus, but only 1 electron on it. We could go even so far as to say this would be a lithium 2+ species. Okay, so that would be another way this problem might be presented to you. But the way it was presented in this particular case is just like this. Calculate the ionization energy for a hydrogen-like atom with 1 electron and Z equals 3 from the excited state of N equals 2. Submit an answer to 3 significant figures. Okay, so we need to think about our 3 significant figures, and we'll have to be careful with that. I'm going to go ahead and share from my document camera, I hope. Here we go. So I wrote down the 2 pieces of information that were buried in our problem. And we want to know the ionization energy, which we can call EI. And we want to know that in electron volts. So let's keep that clear as well. So we need to submit an answer to 3 significant figures. We'll need to keep that in line. How many significant figures does this integer and that integer have? Anyone have an idea? 1? All right, who said 1? I didn't see who that was.
Bella.
Bella, thank you. All right, so there's a single digit. That is certainly true. Does anyone else feel differently, that there are any different number of significant figures?
Aren't there kind of as many as we need to be, as we need them to be? Because it's like an exact value.
Yeah, so Lakin says there's, that was you, Lakin, right?
Yeah.
Okay, so this could be like an infinite number of sig figs too. It's got to be one or the other. Those are great answers. Here we are on our bookends again, infinite and a single digit. So in this case, they are infinite because these, as I said, I was careful with my word choice there. I said these are integers, right? And because they are integers, let's think about where they come from. Z is the number of protons. And by our Dalton's theory, by our definition of the atom, we can't have less than a whole proton. We can only have integer numbers of protons. So we know that this is 3 and it is no more than 3 and it is no less than 3. We know that it's precisely 3. So that has essentially an infinite number of significant figures. And in the same way, when we're thinking about quantum states, or like our energy levels, we know that it can be n equals 1, and it can be 2, and it can't be anywhere in between those 2. So that is also an integer of 2 with an infinite number of significant figures. Okay, so let's go ahead and set up our equations. I gave you this equation just a slide ago. The energy of state n is equal to negative k times z squared divided by n squared. But this question is asking us not for a single level's energy, and it's asking us to think about 2 energies because we're ionizing. So another hidden equation here would be energy of ionization equals the final energy of our electron, which if it's ionized would be at the state infinity, minus the state that we're starting in, which is n equals 2. It was told to us there, so we'll call that E sub 2. Now, lucky for us, we can plug in our values of n, infinity, and 2 to this equation here and substitute that in. So we would get something that looks like E infinity is negative k z squared. And of course, you could plug in your value for z if you were ready, minus a negative k z squared divided by 2 squared. So I just plugged in n for each of my 2 states, final and initial. Okay, and to get my answer, I noticed that dividing by infinity is again 0, right? So this, it goes to 0, just like it did with our Rydberg equation. So our equation simplifies to K times Z squared divided by 4, because 2 squared is 4. Okay, wonderful. So now we can just sort that all out. K is equal to negative 2.18 times 10 to the negative 18th joules. That is our constant here for a hydrogen-like atom. So we can plug that in. Our Z is 3, so that's 9 squared. Okay, so we can go ahead and plug that into our calculator, which I unfortunately don't have a scientific calculator at home with me because I didn't know I wasn't heading back to my office. So if anyone has a help, that would be amazing. Otherwise, I can try to use my phone here. This is hard to do on a phone. Is anyone using their phone on the regular? Okay, I don't see anyone. I don't have I only have one screen today, so. Have to do this one the hard way.
It should be negative 4.9 times 10 to the negative 18th, if I'm right. Something along those lines. I didn't use negative 2.18. I used negative 2.179 times 10 to the negative 18th. So
Okay,
my decimal points would vary. Yeah. Or sorry, my decimal values.
could you repeat your, oh, we got some in the chat here too. 4.91 times 10 to the minus 18th, 4. And that would be in joules. Okay, and we need to know what our sign should be here. We have a lot of sign conventions, but we can think about the fact, I think I goofed up. I think this constant should be a positive value. That was my mistake. So that should be a positive value because we need to input and we need to give energy to the system. So when we talk about how much energy does it take? Well, it takes 4.91 times 10 to the minus 18th joules to get there. And then we have to convert that value, 4.91 times 10 to the minus 18th, into electron volts. Got to go back to our conversion factor, because I don't think we wrote that one down. Let me pull the notes back up. Here we go. That's down here at the bottom. 1 EV equals 1.60218 times 10 to the minus 19th. I'm going to stop there. So we have to do one quick unit conversion from joules to EV, 4.91 times 10 to the minus 18th joules. And we have 1 EV has 1.60218 times 10 to the minus 19th joules. Thank you very much, Mike. 30.6 EVs for our answer. Okay. Let's go ahead and think that one through really quickly. Does that make sense as an answer? 30.6 EV. Well, we know for hydrogen itself, it ended up being around 13.6. So this is a higher value than hydrogen itself, but it's not massively higher. It's in the same order of magnitude. So that actually makes really good sense because we increased our charge, right? This is a Z equals 3. So we have more positive charge in the nucleus. So it's going to be more attracted to that electron and have a harder time. We're going to have a harder time pulling that electron out of its orbit. So 30.6 makes sense. All right, Rachel informs me that the doc cam is lagging very badly. Apologies for that. Please don't hesitate to just let me know if you're having trouble keeping up with what's going on. My computer has been acting up. All my notes are crashed, which is why I have to ask you all to do my calculations for me. I can't keep them open. It won't let me. Okay, so that is what we've got there. Let's head over to our second question. Okay. Now, these are the kinds of questions, and I kind of want to talk you through the entire process on how I think through these. Well, first of all, were there questions on that solution? Did anyone have any questions on how we did that?
Yeah, I think I do.
Mhm.
So I'm not exactly sure how to like ask the question, I think, but can you explain like why you took the like E infinity minus, so can you just like explain why you took the infinity minus the final?
Absolutely. I will try the dot cam this way. We'll see if that goes a little faster. Okay, so Emily asks, why did I set this equation up here like this? And ionization energy equals final state minus initial state. We didn't necessarily have to do that, did we? We could have just used our equation here for the energy of the state and then changed our sign. That would have worked fine too. But when you set it up like this, right, this is kind of a useful way to consider any process like this. And that way we can go from any level to any other level. And in this case, we went from we went from our initial level to our final. This is the reason I set this up like this is because this is another one of those thought processes as we go through our problems that we're going to encounter a lot, where we have some beginning state and some end state, and we want to know the change between them. And so another way to think about ionization energy, this is the change in energy of the electron from a state n to the state infinity. And if we do that, but it looks a lot more like 8 than infinity. Let me try again on that one. There you go. When we go from that way, we can always set up the equation like this, even if we don't have the exact correct equation, right? I knew this tells me the energy of my state, and I wanted to double check that I got the right total change in energy by looking at both the initial and the final states. Does that kind of answer your question, Emily?
Yes, thank you.
Thank you. All right, well, let's set up our next question. Unless there are further questions, I should pause. All right, and here we go. Using photoelectron spectroscopy, the ionization energy of the least tightly bound valence electron on chlorine was determined to be 13.0 eV. Calculate the Z effective for this electron. Okay, so we're off in new territory here, right? This is unusual for us. This is not a hydrogen-like atom, right? It doesn't show that anywhere. And in fact, we're talking about chlorine, which has lots of electrons. So this one is going to require us to think about this ionization energy, right? At least it's still an ionization energy problem. We've got that. So we have to think about this a little bit differently, but let's just kind of start the same way we did last time. We're going to write down the information we have. So onto my paper that I have on the document cam, which you can't see right now, I recognize, but I want you to be able to read the problem. All right, we want to know Z effective. That is our question. We know the energy, change in energy, our ionization energy is 13.0 eV. And we still know our constant, our K, is equal to 2.18 times 10 to the minus 18th. And we know our conversion factor, that's still on our paper too. All right, let's see if we have enough information to do this. Is it a sharp enough view for you all if I switch to if my video's on the document cam like this? Everyone can read that clearly? Can I get some thumbs ups? All right, thank you, Maddie. Thanks, Bella, Ryan. All right, so here we go. We want to know Z effective. We know our ionization energy, that's 13.0 electron volts. And we know what K is, that hasn't changed. So we still have our equation up here. We could use this one again, but let's just go straight to that one. We have, all right, so EI equals E infinity minus E initial. And here, it's a little tricky. We don't know what N is, do we? We haven't gotten there. That doesn't make any sense to us. And that's where our Z effective comes in. So we haven't talked about Z effective. I wanted to introduce it in the context of this problem because Z effective, and often, and again, this is another chemical process that I want to think about, is sometimes we just have the data we have and we want to make it look a little bit like something. So when we're looking for a Z effective, all we're going to say is, I know the energy that it takes to pull this thing off. I'm not even sure what shell it's coming from, so I'm going to just go ahead and give it a try. All right, so let's just plug in our numbers to the equation. So our En is going to be 13.0 electron volts. I'm going to convert that to joules right away. And then I have the rest of my equation up here. I'll just rewrite it here. All right, let's just assume N equals 1. Because we don't know what it is, and we're going to bury that into our Z effective. So we'll write for Z effective, En equals negative K times Z effective squared. And now N squared, dividing by N squared goes to 1. So when we know what Z is and we know the levels, then we can be specific, but when we don't know for sure, we'll call this Z effective. So if I rearrange that equation to solve for Z effective, I can divide both sides by negative K. So negative En over K, and then take the square root of both sides, gives me Z effective. And we can solve. So let's go ahead and put this value in. Just to remind you all that the square root is also the same as taking something to the 1/2. And that should give us our value for Z effective. All right. Just find my square root button here. Okay. I get a Z effective of 0.977. Okay, so that's actually less than 1, right? And that doesn't make a lot of sense to us at first glance, because we should kind of expect it to be around that for hydrogen. But Z effective is just telling us how much it. This is this idea. Z effective is a. Oh man, I'm floundering here. Give me a second. Change my video back to me. So Z effective, we have. When we know Z, right? So the hydrogen-like problem with a single electron, we have our electron that's close to the nucleus, and whatever that charge on the nucleus is exactly the charge that the electron is going to feel, right? That's going to be the interaction. The charge on those two charges are going to have that attractive force. But when we have more than one electron, Ashley, thank you for your question. I goofed up that constant before. That constant should always have a plus sign in front of it. When we use it for this equation, the K itself should have a positive value because we're talking about the energy of the electron in state N. So getting back to the idea of effective nuclear charge, the problem with the Bohr model, the reason the Bohr model falls apart is because if we have more than one electron, we can't say that electron A or electron B is feeling all of the charge because they can get in each other's way, right? This is a concept we'll call shielding, and we're going to get into more on shielding in a little while. And so as a workaround, we just say, okay, what does it look like by the data? So if I take a photoelectron spectrum and I shine it with UV light at 13.0 eV, and it knocks off the electrons, well, then I can say that that electron feels a charge of a certain amount. And it feels a charge of about 0.977 in this case. That was what we calculated. And that makes sense, right? It took 13.0 electron volts. We know that a 1-to-1 charge ratio gives us 13.6. And so knocking that off, we should expect then that an electron in the chlorine atom should be slightly less than what it feels. Rachel asks, shouldn't Z effective always be an integer? And in this case, no, Z effective does not need to be an integer. There's different ways to see Z effective. For a problem like this, it can be a non-integer number.
Will you go back to your work just for a minute or two, just so I can see it, please?
Yes.
Thank you.
So in other words, the reason it's not always an integer is because when there's other electrons in the way of the protons in the center, right, those electrons are stealing a portion of the charge. So Z, like we had up here, must always be an integer because you can't have partial protons. But what we're saying with Z effective, right, and that effective word is doing a lot of work here, is we're saying that the amount of charge that feels, right, the amount of charge that electron feels is less than a full proton's worth of charge. It's some portion of that proton's worth of charge. All right, we're going to come back to Z effective and this idea of shielding in more detail later. So for now, I just wanted to set you up for thinking about ionization beyond just the hydrogen-like atom. We're going to come back for more on that. All right, so with that, I'm going to open up an assignment on Chem 101 and also a attendance. So today's attendance code is 7552. All right, so it's just one quick practice problem. Breakout rooms are available, so I'm going to go ahead and open those up, and we'll send you all to breakout rooms to work on that problem on Chem 101. Please do call us in if you have any questions on how to work it. Are there any questions before we go? Open the rooms. All right, here they go.
There's no room 12, Graham.
Okay, hello again, everybody. Sorry if that took a little longer than expected. My internet completely crashed as soon as I sent you off to breakout rooms. So I am back and working. Right, let's go ahead and get back to the lecture. Did anyone have a question they wanted to address from that practice exercise?
Was that one kind of like similar to the lithium problem that we?
I hope it wasn't exactly the same.
I think it was.
Was it the same
We were
for,
doing it.
was
It
it the
was
same for
exactly the
everybody?
same.
Oh, it was supposed to be an algorithmic one where it changed different parameters, but it apparently doesn't work like that. So great. Well, super easy practice. We'll what we call that, a break instead of practice. Sorry, everybody. Let's finish up. We got about 10 minutes left. Let's move on to some new material. I think we've hammered ionization energy into the ground. So I'm going to go ahead and launch the notes again. Okay, here we go. So an interesting thing comes about when you start looking really carefully at electrons and the light that interacts with them. And that has something to do with what I said in the recap at the very beginning about how the smaller your wavelength gets, the harder it is to conceive of things like a wave. It starts to look like a particle. And when you really dig into the Bohr model and start thinking about electrons zooming around a nucleus, that model really depends on the electron being a particle. And so for a while, physicists worked really hard to try to figure out, okay, if it's a particle, then where is it? We should be able to locate it and we should be able to see it. And they had a very hard time designing any experiment that would allow them to do that. And eventually, Werner Heisenberg comes up with a theory to explain why that's such a problem. And it has to do with the fact that these electrons are like particles and they're like waves. And that is, as you get, right, if we want to see where an electron is, zooming around its atom, we have to have a way to interact with that electron that's got enough resolution for us to actually pinpoint its position. The way we usually do that is by using light, but now we know that light, as we try to zoom in and further and further and further and get to tinier and tinier wavelengths, right? We need a small enough wavelength that we can look at things on the picometer scale. These are teeny tiny, right? In order to do that, it has to have super duper high energy. So we run into this problem where if I want to look at something really, really tiny, I need a really, really short wavelength, but I automatically have way too much energy. And we see with ionization energy and what we just did, if you do that and you look at the electron and try to find where it is, you're going to blast it off into outer space by looking at it precisely with its position. Okay, another way to put that is in math form, like shown right here, delta x times delta p or cross delta p, where p is the momentum, mass times velocity. There's a fundamental limit to that. The delta sign here is our error sign. That's how much we don't know about x, right? In other words, it's kind of like significant figures, right? We can get down to a certain number of significant figures. But the error in x times the error in the momentum has to always be this fundamental, at least h over 4 pi. Yeah, this is the Heisenberg uncertainty principle. We know H, that's still Planck's constant. So we have a fundamental minimum uncertainty. We know exactly it has to be at least this uncertain. We can only know it to this limit. We can't know it any more precisely. We can either know where it is or how fast it's going. There's no way for us to know both of those things. Okay, and so, you know, some of the text here is a little less important for our take-home message. The take-home message is that the uncertainty of its position is bigger than the size of the whole atom, right? So if you're trying to measure this specific place, it falls right apart. We need a new theory yet. Bohr's model did a lot of good for us. It explained to us these emission spectra and absorption spectra. It fit the Rydberg equation really well, but it wasn't quite enough to get down to that fundamental, let's find where the electron is. And Werner says, no, we can't. You can't do it. It's impossible. So that leads us to needing another new theory, and enter two more scientists from that era, Paul Dirac and Erwin Schrodinger, who come up with this idea of quantum mechanics. It's kind of our new picture of the atom. It's a new mathematical treatment in which you take into the account the wave-like properties and the particle-like properties of matter. Okay, this is what the fancy equation looks like. I'm going to blast through this because I don't expect you to know how to use this kind of stuff. It simplifies way down to this funny equation that looks like this: H hat times psi equals E psi. And Schrodinger says, you know, as we delve deeper into the atom, it becomes less tangible and more mathematical. And so at some point you kind of have to like learn your differential equations and do lots of calculus to get into this kind of stuff. If you're interested in it, you can take Chem 470 with Professor Fleshman, who you'll see on Friday, and get all into this. You can derive this equation and you can really put the Schrodinger equation to use. For this class, I'm going to go ahead and we're going to zoom out. We're going to say, okay, we got a new theory. It's highly mathematical. It comes from this new picture of quantum mechanics. Let's see what the results end up looking like. Okay, so there's our equation. Basically, this says electrons act like waves, but we can still learn things about them, even though we can't find their exact position. This psi here is called a wave function, fancy word for a piece of the equation, all right, that describes the electron. And actually, it's very mathematical. It doesn't really mean much physically. But then we figure out that, as it turns out, if you square the wave function, that math turns into something a little bit more useful, right? There's only one bolded word on all of these three slides that I've showed you, and that is this word right here, orbitals, okay? So once we finally get through all this in this new theory, we get down to our answer for where is the electron, or what does it look like? And the best we can do is these things called orbitals. Orbitals are where an electron is statistically likely to be at any given instant. We have to go into statistics now because we have that uncertainty that is inherent to these processes. Okay, some people might look at this or refer to these as electron clouds, orbitals, right? So this picture here is if you kind of do a simulation and you simulate the position of the electron based on the probability, and you do it 1,000,000 times or however many times there are dots here, you get something that looks like this. It looks kind of like a cloud with a lot towards the middle and then getting more and more diffuse as you work your way out. Okay, so the take-home lesson from those three slides is from the Schrodinger equation, we learn where the electron is likely to be, not its exact position, but a likelihood of where it can be. And we can also come from that, this E term, what energy it can have if it's likely to be there. All right, so practically speaking, how does this work for us? Well, we're going to dig into orbitals a little bit. We're going to see what these orbitals end up looking like, and what the, right after they do all the math for us, we'll see what their results look like and how we can use them without having to know, differential equations. So atomic orbitals are like these three-dimensional shapes. We talked a lot about standing waves. These are like a three-dimensional standing wave, and they have different shapes depending on what harmonic they're on or something like that, right? And so the shapes are going to impact that. We're going to start with a kind of orbital called the s orbital. This is simplest orbital, And the letter S is kind of a historical thing. We're just going to remember them as S. You could maybe use the mnemonic that S stands for spheres because they're all spheres. All right. And another thing that you're going to notice is that these are the closest thing to Bohr's model, because these are just shells that get further and further from the nucleus as you go up with this thing called principal quantum number. In other words, as the energy of the electron increases, it gets further and further from the nucleus. This is the kind of thing we're used to thinking about. So they're spherical. You have pictures that look something like this. And here's that electron cloud depiction where we see lots of probability of finding an electron towards the center near the nucleus and less as you go out. Also point out in the 2s and the 3s, there's a couple spots where there's no probability at all. This line right here, and then that line here, and that line there. Those are called radial nodes. We'll talk more about those as we continue on. Okay. We also have other kinds of orbitals, the p orbitals. They have this shape here. Sometimes those are called the dumbbell orbitals. And we have d orbitals, which are the double dumbbells. I've heard of that, right? The dumbbells being like the things you lift, you know? Okay. And there's some rules on these slides. Don't worry about those rules for now. We're just going to concentrate on the shape for now, the p orbitals. There's 3 of them. There are 5 d orbitals. This all has to do with the math that's behind the quantum mechanics. All right. But for now, I just want you to notice the shapes and the number of lobes, right? So s orbitals are big spheres. P orbitals are now dumbbell shaped, kind of like 2 spheres next to each other. And if you look really carefully, you can see that there's a plane that separates the 2 spheres, right? So if I look at this one closely, our 2px orbital, right? The 2 spheres are kind of aligned along the x-axis. And if I make a plane with the z and the y-axis, it cuts the 2 in half. That's called a planar node or an angular node. And when we look at the d orbitals, we can see it's kind of the same thing, but now we have 2 planar nodes. One along the z, y, and one along xy for the d, x, z one for here. All right, so everyone's got to run. We will cut it off there and we'll dive back in with more orbitals next time. But for now, there's S, there's P, and there's D. We'll pick it up from there next time.
Thank you.
Thank
Thanks,
you.
everybody.
Thank you.